right. Hello and welcome back to the lecture. As I told you, I will keep bugging you about the course evaluation. For CS 451, 651 section, only 10% of the students have filled out the form. So please complete the survey. It won't take that much time. And by the way, this is not one of my evaluations. All right. And I'm going to remind you again about, get rid of this thing here, that your project is due in about 2 weeks now, so we don't have much time. So please start working on your project if you haven't done that already. Okay. Let's continue talking about mutable state. If you remember, we said the difference between this topic and what we learned before is that previously we were working with read-only data mostly, and our writes were limited to append only. And it was not like a random read or random write, but in some cases, that's what we really need. So we want to figure out how to handle that. We talked about different algorithms last time, and we introduced the idea of NoSQL, and today we want to talk about some fundamental concepts in this domain. Some motivating scenarios. This is very interesting, especially nowadays in the context of cryptocurrencies. That basically money should not be created or destroyed. So on the network of Bitcoin, no transaction should create new Bitcoins except mining process, which is something different. And also it should not destroy money. So if somebody has like 1 Bitcoin in his or her wallet, that person should not be able to send that 1 Bitcoin to multiple people. Right, so we should. So basically, that transaction should not create money. This is also called double spending. So you have like 1 Bitcoin and you spend it multiple times. So that should not happen. So how can we prevent this in a distributed system? Sometimes you might have seen something like this, that on a website you basically do something. For example, you update your shopping cart. For example, you remove something from it, or you do something else on that website. And if you, for example, go to another page or refresh, you see that still it's not updated. So that's basically a problem. And finally, if you wait, you will see that, okay, for example, the item that you removed from your cart is finally gone. But it sometimes doesn't happen instantaneously. So we want to figure out what's going on in this lecture. So we have another kind of funny scenario here. So Alice removes mom from the list of people who can view photos, and then Alice posts embarrassing pictures from spring break. Now the question is, can mom see these photos? Or you have probably seen this. You unsubscribe from a mailing list, but you still get emails for a while, and eventually it's gone. So in all of these scenarios, you can see that there is a delay from the time something happens from the time that thing takes effect eventually. So to understand these things better in the context of distributed systems, I'm going to introduce 3 topics. We kind of mentioned these to some extent during this term, but we want to see the official definition. And after we learn these 3 concepts, I want to present a theorem, which is really interesting, that kind of links these concepts to one another. Okay, so please make sure you understand these 3 simple concepts, because otherwise you cannot follow this lecture. So the first concept is consistency, and I'm going to explain this in terms of an example. Suppose that we start a new bank, okay? And we call this bank big data bank. We call it BD. TD will sue us. So, and basically to provide service to the to entire Canada, we place multiple servers in different provinces and territories. Okay. Now, let me explain consistency in this example. So we have a network of computers. So we have a distributed system. And I will deposit some money, the first transaction in BD Bank. So I deposit $1,200. Okay, consistency is this. It says, if I want to retrieve my account information, if I want to figure out how much money I have in the bank, it should not matter which server I query, right? All of them should see the same image. All of them should see the same amount in my account. Consistency is defined as all nodes should see the same data at the same time. For example, if I deposit $300 more, all of these nodes should have the new amount, which is $1,500. It should not be the case that some of these servers are lagging behind and they still show the old value, which is $1,200. So that's consistency. So there is a value, like a key value pair kind of thing. So all of them store the same thing. It should be exactly the same after an update, after a write. So if I deposit money or if I withdraw money from my bank account, all of them should reflect the same amount. That's consistency. The next concept is availability. So when we have a distributed system, it's possible that one of the nodes die. The server crashes, the disk crashes, or power outage, or something like that. So one of the servers die. So in this case, I think the server was frozen because it's in the Northern Territories. So we lose that server. Now availability says node failure do not prevent survivors from continuing to operate. Meaning that if one of our servers die, the rest of the servers should continue operating, right? So our Toronto server should keep working. It should not be like, oh no, one of the nodes is gone, we should stop. No, availability means we continue operating despite that failure. And don't confuse this with the next topic that I'm going to explain. This one is availability. It's talking about node failure. So if a server goes down. The next concept is partitioning tolerance. This one talks about the links between these servers, not the servers themselves. What is partitioning tolerance? This is the third concept and the last concept. It says, if you have a network issue in a way that your network is partitioned into two or multiple partitions, the system should continue operating. For example, here, if my link between Manitoba and Ontario breaks, and because there's no other link between the right part of the network and the left part, I have partitioning, right? So these guys won't have any way to communicate with these guys and vice versa. So this is partitioning. So it's not talking about failure for a particular node, that was availability. This is talking about links, breaking links in a way that the network is partitioned. So partitioning or partition tolerance means, can we continue operating despite having partitions? So the system continues to operate despite network partitions. So this is partitioning tolerance. So that's basically the three topics that I wanted to explain: consistency, availability, and partitioning. Now I'm going to present a theorem that links these concepts. Is there any question about these concepts. Are we clear about what they mean? Please let me know if I need to explain something better or again. So everyone is clear about these three concepts? All of them are good properties, right? We like to have all of these properties in a distributed system, but unfortunately, we cannot. And that's the cap theorem. So the cap theorem basically links these concepts. So the cap stands for basically these three concepts: consistency, availability, and partition tolerance. It says a distributed system can satisfy any two of these guarantees at the same time, but not all three. So the cap theorem says you cannot have all of these three at the same time. And I will show you a simple proof of this in a second. But another way to present this is that, okay, we have three properties: consistency, availability, and partitioning. The cap theorem says this part, which is like having all three, is not possible. And you should pick two. When you design a distributed system, you should pick, like, what do you want to have? We can have consistency and partition tolerance. You can have availability and partition tolerance, but you cannot have all three of them at the same time. That's not possible. That's the cap theorem. Very simple, but significant impact, right, for system design, meaning that, like, you cannot even go after achieving all of these three. Any questions about the cap theorem? Okay, the class is very silent today. So why can't we have all three? That's the question that we got. That's a good question. So why? Why is that the case? Show us the proof. That's a good question, because that will take me to my next couple of slides. But before that, let me explain these combinations a little bit more, and then I will provide the proof. So when the cap theorem says we can pick 2 out of 3, that means that there should be 3 kinds of distributed systems, right? Because we have 3 different combinations, right? That we can pick 2 out of 3. That's like 3 different combinations. So it means that, do we have like 3 kind of distributed systems? Yes and no. So let's see. So there are systems that pick consistency and partition tolerance, meaning that they give up availability when there is partitioning. So if they detect that there's a network problem, they stop working to protect consistency. An example of that is Bigtable and HBase that we learned recently. You may ask, before I move on, you may ask, like, why? Well, that's their design philosophy. There are systems that are not like that. And as a result, they have different properties and different behaviors, different performances, okay? Another example is AP, so availability and partition tolerance. An example of that is DNS systems. So DNS is basically the service that translates domain names to IP addresses. If you have created a website yourself and you try to set the IP address in DNS, you will notice that it is not consistent at all. It may work for you after you set it, but you ask your friend to check your website and he or she says, well, it says the page cannot be found, the IP cannot be translated. And that's because DNS is a distributed system, and when you make a modification, it does not propagate immediately. It does not guarantee consistency, meaning that some of the servers have this new update, but the rest of them don't have the update. And it's actually a very problematic issue sometimes. You create a new website, even after 24 hours, sometimes you see that in some regions of the world, they cannot access your website because their DNS has not been updated. So it's available, but it's an available system, meaning that if a DNS server gets disconnected from the rest of the DNS network, it keeps operating. It may not be right. It might be wrong because it's disconnected from the rest of the network. So if there has been a change, there was no way that this server could know about it. But it keeps operating. It keeps responding to based on the latest information that it has. So it picks availability over consistency. Now, that's a third one. So there is a third one, and that is consistency and availability, and we give up partition tolerance. Well, if somebody tells you that he or she built a consistent and available system, he or she is lying to you because this is not possible. So basically, when we said you can pick any two, there is some restriction there. We cannot pick consistency and availability because partition tolerance is basically part of any distributed system. So it's like P in CAP theorem is selected. It's mandatory. Let me explain why. Basically, if you say my system is consistent and available, the claim is like this, that my system will never be partitioned. This claim is wrong in any distributed system. Let me give you a simple example, like the simplest example possible. Suppose that we have two computers, two servers in the same room. Okay, this is like the simplest distributed system. They are not in different continents or different data centers. Two servers in the same room, connected directly via switch. So it's not going through so many routers that can fail, just one switch that connects these two machines. Even here, if I claim that this link will never break, that's a lie. How can I say that? The switch can fail, the cables may fail, the network cards can fail. And then these two servers become partitioned. So, and especially in real life, I mean, if it's a distributed system in like data centers, it's even more complex. It goes through multiple switches. The network is much more complex. It might be across different data centers. So there are so many things that can go wrong. Even on my simplest example of two servers in the same room, I could not guarantee that partitioning doesn't happen. And obviously, in a much more complex system in real world, it can happen anytime. So basically, that property is like, it's not like an option that we can pick, but rather it's the property of any distributed system. So when we said you can pick any two, that was a lie. You can basically pick consistency or availability because P is picked for you already as a property of any distributed system. And that's why there's no system in this category. That's why I used a screenshot of Mission Impossible and Tom Cruise there. So that's not a real system. So CA is not possible for that reason. Questions? So all of this is correct if the CAP theorem is correct. Again, still I haven't explained like why CAP theorem is right. I will. So because of basically this property that we saw, so systems can be either consistent or available. They cannot be both. And this has basically divided the database community, right? So we have systems that are consistent, so they pick correctness, like MySQL, for example. And then there are systems like many NoSQL systems that pick availability. They continue to operate and they may be incorrect for some time, for a while. They may not be consistent for a while, but they choose to continue to operate. Okay, so we can basically divide the database systems into two groups based on the CAP theorem. So that's the impact of the CAP theorem. Okay, so the proof that you were looking for, it's not a very difficult proof. It's more like a visual kind of explanation. All right, so let's simplify the system. I want to show that why CAP theorem is correct, why we can only pick 2 out of 3 properties. Suppose that we have 2 servers. Okay, I'm simplifying things. And for now, the assumption is that these 2 are partitioned. So the network connection between A and B has broken. The system, and then I explain a sequence of operations, and I show that the CAP theorem is right. In this example, we have a write request to server B. Okay, so that a star indicates like some data that we have to write to B. And now we have a read request in the system from server A, which is disconnected from server B. So obviously it cannot have the new value, the star. It still has the old value, which is the square. Okay, so if A responds to the client, then the system is not consistent. Do you agree? Because the latest data is a star, that thing that we have written to B, but A does not have this new value. And if it responds to clients, it will respond with the old value. So that's not consistent. We said consistency means all nodes see the same thing in the network. It's not the case here because of partitioning, because A and B are disconnected. Makes sense? Now you will say, okay, that's the problem. We should not respond to the client because we are disconnected. So what you can say is, okay, if we have a case like this, if A detects that it's disconnected from the rest of the network, then if there is a read request coming to A will say, hey, wait, because right now I don't have a connection and I may respond with the wrong data, and if that will be inconsistent, so please wait until my network connection is restored. The issue is if you say that, then the system is not available. If you tell the client that, hey, you have to wait now, so there's no service for that client. So then it's not available. So as you can see in this scenario, the only way for this to work is to restore the link between A and B so that that write request is propagated to A so that A can respond with the updated value. But this assumption is based on the fact that there's no partitioning, which is not correct. That's not true, right? The link can break, as I explained, even in the simplest case, the connection between 2 networks, 2 computers in the same room can be interrupted. So that's basically a visual and simple proof for the CAP theorem. Are there any questions? Okay, got a question. So can we not have ABC, for example, where A and B are disconnected and C becomes the medium for connection? So if I go back, so the question is something like this, if I understood it correctly. So the question is, let's assume that we have another node like C here, and then this is like a proxy that can pass the value from B to A. Sure, we can have something like that, but in this case, we don't have partitioning because A and B are connected via C. When we say we have partitioning, it means that there is no node C that can connect A and B. So they are truly disconnected, right? So A has no way to talk to B. So basically, by introducing C, you're again assuming that we don't have partitioning. But what if C goes down? What if the length goes down and A and B are disconnected? So that's the idea. We can think of this, the simplest case is that there is a network and then one particular server gets disconnected from the rest of the network because its internet connection is interrupted. So that single server A has no way to talk to other servers. So it's partitioned. Good question. Other questions? So everyone is an expert in cap theorem now. All right. Let's talk more about consistency. I have been talking, the definition I used was a bit loose because we have different types of consistency. What I was referring to until now was technically strong consistency. What does that mean? It means after the update completes, any subsequent access will return the same updated value. So in my bank example, if I deposit some money, it means that, okay, I had $1,200. Now I added $300 more. Now my new account balance should be $1,500. And that's a write. So that's basically when it says after the update complete. So I do a transaction that's complete. Now, after this transaction, all servers should have the same value. So if I query my bank account from a different ATM now, I should see the new balance, right? So any subsequent access should return the same thing. So you write and then you perform a read. It should be the updated value. That is a strong consistency. So that's what we were loosely referring to as consistency. So it has a more concrete name. So that's a strong consistency. And some meme or jokes here for you. So The Rock is pretty consistent, the strong consistency across different movies. These are 3 different screenshots from 3 different movies, and he looks the same. So he is very consistent in these movies. Or some single people are very consistent in their relationship status. So doesn't matter when you query them, they're still single. So that's a strong consistency, okay? How can we implement a strong consistency? The different techniques. One common way to implement a strong consistency is called two-phase commit. It's very simple. It has a coordinator and subordinates. So it's basically a master-slave kind of architecture. How does it work? So we want to change something. We want to, for example, update a value in the system. But we want to make sure these subordinates are different servers, like 3 servers that I have in the system. But when I want to perform a write, and I want to make sure that all of them gets the recent value. Otherwise, I want to say, okay, go back to the previous state. I do not want to leave the system in an inconsistent state. Okay, either everybody performs this right or we revert back to the previous state. This is what we want to do to implement a strong consistency so that we guarantee that, okay, if we write something, everybody has the same image. So if there is some subsequent read request, they have the updated value. How is it implemented? The coordinator first sends a prepare request to everybody. And it waits to get a yes from all of these slave servers. What is this prepare request? Whenever you want to do a transaction, you want to update something, you need to get access to some data structures. So you may need to obtain a lock before doing so. So basically, in general, in order to perform the write, you need some resources. In most cases, it's a lock that you need to get in order to be able to perform the write. So when the prepare request is received by the servers, they make sure they have the resources to perform this request. They don't do it yet. They are just preparing for this transaction, for this action we want to do. And if they are prepared to do this, they send this yes message to the coordinator. If the coordinator gets a yes from everybody, it goes to the next phase and it sends a commit request to all of them. Now it says, okay, good, everybody is ready, go ahead and perform what you were supposed to do. At this time, they actually do the write and they send back an acknowledgement. So they act it, say, yeah, okay, I did it. Now I've written the new value. Yes, yes, yes. And if the coordinator receives an acknowledgement from everybody involved in this process, then it says, okay, it sends a done message saying that, okay, everybody could successfully update. We are good. We are done. We could update. And you can see that the system is in a consistent state. Now, things can go wrong, obviously, and that's why we have this process. And the name two-phase commit is coming from the way it works. It has two phases. It has the prepare phase and the commit phase. Let me show you an example where things can go wrong. So the coordinator sends the prepare message, and we get a no, or we don't hear from one of the servers, because there was a problem on that server, or it could not get the lock, or something like that, or it's dead, or it's partitioned from the rest of the network. So for some reason, we do not get a yes message back from that machine. When that happens, when the coordinator detects that it's not getting the response from one of the servers, it sends an abort message saying that, hey, forget about the prepare message that I sent you. Just ignore it. Just release the resources that you have. We are not going to do this. So as you can see, again, the system is in consistent state because it's the previous state. You could not perform the write, but everybody sees the same image. This abort can also happen in the next phase. I don't have the graphics for it, but you can imagine that we get a yes from everybody, and then the coordinator sends the commit request to all of them, but we don't hear an acknowledgement from one or multiple servers. In that case, again, it aborts. It's a little bit different because if you want to abort in the next phase, some machines have already implemented the update. So they updated the value, but the system immediately goes back to the previous state. The coordinator says, hey, someone could not perform the write, go back to the previous state. And they will revert back. They basically undo what they have done to go back to the previous state. So got a question, isn't this the three-way handshake? Yes, kind of. But I think the three-way handshake is like used in so many different contexts, like security stuff, things like that. But probably the same kind of, at the very high level, same idea. So rollback, yes, rollback. We go back to the previous state if somebody cannot perform. If somebody cannot commit, we go back. But how can we go back? There are some assumptions here. So basically, the assumption is we can go back, meaning that we keep a log of what happened. So before we perform a write, we basically log this operation or transaction, and we say somewhere, okay, we are going to perform this write, and this is the previous value. And then we do it, because the coordinator may ask us to revert back. So we have to know what was the previous state. So here the assumption is that we have persistent storage so that we don't lose the stuffs. And also we have the write ahead log. We talked about WAL in previous lectures in HBase, if you remember. So this is a logging system that stores the operations before we actually commit them. And one application of that is we can revert back to the previous state. And the other assumption is that WAL is never permanently lost. So there are two main limitations for this system. It's blocking and slow, right? So it sends a prepare request. So so all of those servers grab the lock and they wait for the commit request to come. And these are like network operations. So at least several milliseconds is passed by the time you receive the commit request. So you have to hold on to all of those resources for a long time. It's a blocking operation, so it's extremely slow. The second limitation is that this is a centralized approach to a distributed problem. So you have a coordinator. What if the coordinator dies? That's a serious problem. And there has been a ton of research on this topic. Okay, how can we get rid of the centralized coordinator architecture? And that's why we have 1 million papers on distributed consensus algorithm. Okay, and I'm going to talk about this a little bit. So we want to get rid of that centralized approach. So there's, in this architecture, there was only one person, one server that was coordinating everything. And that's dangerous because that server can die. So the idea behind distributed consensus is that we want to come up with an agreement in a distributed fashion without having to rely on a particular machine to decide for us. So suppose that this is the current state for 5 servers, and then one of them want to perform a change, okay? Again, no centralized point, so this can be any node. So this node wants to do something. For example, it might be like, let's change the value of X. How can we do this in a distributed fashion without relying on a single server? Or let's execute a transaction. The idea behind distributed consensus algorithm is that after some time, these servers should agree on something in a distributed fashion. And they basically go to that next state. All of them agree to move to that next state. But there are a ton of examples here. It can be like a leader selection, because in many algorithms, we need a leader and then some slave machines. So how can they pick a leader without having one server picking one? How can they do this in a distributed fashion? That's the topic, and there's a ton of research on this. And Paxos is probably the most famous algorithm in this domain. And I will explain Paxos in the next few slides, but at a very high level, very simplified version of it. So how to agree on something in a distributed fashion? For example, we are a group of friends and we want to watch a movie tonight and we want to agree on what to watch. This is exactly what Paxos can do for us. So we want to decide something in a distributed fashion, meaning that we don't want to rely on a third person to tell us what to watch. No, there's no one to coordinate us. We want to decide ourselves. How can we do that? So I need to explain something. When I say we need to decide about a movie to watch, it's not like we have preference. We just care to agree on something. We don't care what option it is. are we going to watch Money Heist tonight or Breaking Bad? We don't have any preference. We just want to decide on something that everybody agrees on. That's the problem. That's the idea. Okay. So then don't be confused, because in reality, sometimes the nodes have preferences. That's not the case here, right? They don't have a preference. They just want to come to a conclusion. They want to agree on something, and it doesn't matter what that thing is. They want to make sure they are consistent, right? So this is the Paxos, the distributed consensus algorithm, very simplified. So suppose that we have like 5 nodes, and here we want to decide on something. For example, which movie to watch tonight. The way this works is like this. So one of the nodes, again, there's no centralized point, right? So one of the nodes will try to convince the rest of them, okay? And this may work and may not work. Again, it's not like we say, no, I don't like that movie. No, it's not like that. It's like we want to agree on something. I don't care which one it is. So somebody wants to suggest one of these movies to see if they can convince everybody and it can get an agreement from everybody. So it has 2 phases, similar to 2-phase commit. What it does, first, that node sends a prepare message to everyone else. Okay, saying that it's like somebody in our group says, I have a suggestion. He or she hasn't said what movie, but it's just, okay, can I talk? Can I suggest? That's the prepare message. It's saying that, hey, I'm going to suggest something. Are you okay with this? And if these nodes haven't promised to any other node before that, they say, yes, sure, go ahead. And that's called a promise message. Okay, go ahead. What do you want to say? Then 3 says, sorry, before I move on, in order for 3 to move on to the next phase, it needs majority. Okay, so 3 has a vote. In this system, it needs 2 more votes at least to proceed. Okay, so if it gets majority, so if it gets at least 2 promises from other nodes, they are in majority. For example, if it gets a promise from 1, 2, and then 3 itself has a vote, so it's like 3 to 1. So it can move on to the next phase. So it's like most of the people in our group agree that that person can suggest something. So he or she hasn't suggested anything. It's just giving permission or agreeing to listen to somebody. In the next phase, it actually suggests. In the next phase, it says, hey, accept Money Heist, for example. How about watching Money Heist? And then other nodes will respond with an okay and what it was suggested. They say, we are okay with Money Heist. In this case, again, if we have majority, it's done. Okay, so if it gets a majority vote, it's basically committed, and we have came to a conclusion in a distributed fashion. But as I said, it's a very simplified version. There are so many things that can go wrong, but Paxos has a way to handle those situations. And if you take a real distributed system, they will probably talk about Paxos probably for the whole session or even multiple lectures, because it's a very complex system. What I wanted you to learn here is to understand that there are distributed consensus algorithms that can decide about something without having to rely on a third party, on a coordinator. So basically, it solves one of the limitations of the 2-phase commit, which is what happens if the coordinator dies? Well, in a distributed consensus algorithm, there's no coordinator, so we don't have that problem. Any node can initiate a suggestion, and then other nodes, depending on the algorithm, they say, okay, have you promised to someone else before? If no, it's okay, cool. We say, go ahead, suggest, and then we confirm, and it works like that. And obviously, so many things can go wrong. The suggester can die, one of the nodes can die, and things like that. And if you take a real distributed system course, they will explain how that works. Do you have any questions for me before I move on? So this was a strong consistency, and what I explained, basically two different approaches for implementing a strong consistency, and that is the centralized approach, two-phase commit, and then Paxos, which is an example of distributed consensus algorithms. So their goal is to achieve a strong consistency. Now, we have weak consistency as opposed to strong consistency. And if you look at the definition, it's very lame, right? It says it's not guaranteed that subsequent access will return the updated value. What the hell? How is this useful, right? It's completely against consistency. So yeah, I agree, it's useless. But it's interesting because a special type of weak consistency called eventual consistency is actually very useful and became a hot topic, and it is still a hot topic. Many systems actually use eventual consistency, and despite not providing a strong consistency, it became so popular. Let's explain first what eventual consistency is. It says it is guaranteed that if no new updates are made to object, eventually all accesses will return their last updated value. Okay, explain that in English to me. So it says if you have a write request in the system, if you perform write, and then we have read requests, it says that, for example, if you read it immediately after write, you may read the wrong value. There's no guarantee because it's type of weak consistency. If I could guarantee that you read the updated value, that would be a strong consistency. But if you give it time, eventually that update will be propagated to the entire system and all servers will have the same image of the system. It eventually becomes consistent, but there will be a period of time that the system is in this inconsistent state because the update hasn't propagated to all of the system. That's why it's called eventual consistency. If you give it time, it becomes consistent. It is not a strong consistent because there is a time that servers have different images of the system. That's interesting. Let's review some examples to see if we should use a strong consistency or we can live with eventual consistency, which is a weaker version of a strong consistency. So in the first example, let's talk about designing ATM machines. Okay, for our bank, what was it called? BD Bank. We need ATM machines, okay? And we need to figure out what type of consistency is good for the ATM machines. So, for example, if an ATM is disconnected from the rest of the network, what should we do? Should we go with consistency? Should we say, hey, sorry, we cannot service you. So this ATM is out of order at this time. It cannot work. Or you say, no, it's fine. You keep working. It's available. The service is available. So if somebody wants cash, if someone wants to deposit, it's okay. We can continue operating. So, and we can eventually update this. It's okay that we are in this inconsistent state for a while. So which one do you think is better? Strong consistency, meaning that we say, hey, sorry, no service. Because if I accept this transaction, I will be in this inconsistent state because I cannot propagate this information to the rest of networks. Or maybe something has happened that I'm not aware of because I'm partitioned, so I cannot service. Or you say, no, we can keep working and we can eventually talk to the rest of the ATMs and we update each other. So which one is better, do you think? Actually, I have a poll, so let me launch it. There you go. So what type of consistency is better for ATMs? Strong consistency or eventual consistency? So basically, the CAP theorem says we can have either consistency or availability. Now that we know all of these different types of consistency, the CAP theorem is referring to a strong consistency. It says you cannot have a strong consistency and availability at the same time. But you can have eventual consistency because it's not a strong consistency and availability. That's possible. Meaning that you are in this inconsistent state for a while and eventually you restore your link and you get the updated value, or you update the rest of the network. So it's possible that to have eventual consistency plus availability. So let's see the results. All right, so I got around 10 responses, 11 now. 64% say strong consistency. And 36% say eventual consistency. So that means 2/3 of you are wrong. So it's counterintuitive, right? That's why I had the poll. So you're right. In theory, it's money. It's money, right? So we should have a strong consistency because if this ATM machine is disconnected from the rest of the network, what I can do is that I empty my account from another ATM, and then I come to this ATM, which has no idea because it couldn't receive this update, and then I empty my account again. So it's bad. That's why most of you said we want a strong consistency. But things are different in practice. Although strong consistency appeared to be a natural choice, as almost 70% of you indicated, in practice, availability beats consistency. The bank says, for me, it's more important for my service to be available, although I'm in this inconsistent state for a while. Because if I don't provide any service, I lose all of my customers. At the cost of, sure, there might be inconsistencies. Somebody might be possible to withdraw money twice because of this, for example. But I live with it. It's okay because availability is better. Because I don't want to stop my service to 99% of my customers because 1% of my customers may want to cheat the system. I prefer availability. Amazon prefers their website to be up and functional, although there might be some inconsistency. They don't want to shut it down because of a problem as much as possible. So availability is very important for businesses. No availability, zero money you can make because there's no service. So availability is very important for them. So let's conclude. So are you saying that in practice, if ATMs lose their connection to their to other networks or like the other servers, they keep working? Yes. Okay. If you get arrested, please do not call me, okay, to bail you out of jail. So yes, it's possible. It's possible. If it gets disconnected, it still works, and that means that you can empty your account from other ATMs and then you withdraw more money from the disconnected ATM. Yeah, that's most probably possible. But you may say that's bad for the bank. Well, it's the bank. First of all, there are some limits. The reason we have withdrawal limits, one of the reasons there is a withdrawal limit from ATM is this, that, okay, if there is inconsistency, if somebody wants to cheat the system, we'll limit the effect. So it says, hey, You cannot withdraw more than $200. So that's you basically limit your loss. Sure, someone can empty their account and they can withdraw more money, but there's a limit on it. That's one thing. And the second one, it's the bank, guys. They will get the money eventually from you. Because sure, you go to a negative balance. What happens for the bank? Tomorrow they figure out that you withdraw more money. They will get that money from you plus some fee for going over your limit. They will even make money from that problem. So don't worry for the banks, okay? So they are okay with this, even if it happens. They won't even lose money. They will probably get more money from it. And they had their service up and running, so that's excellent for them. But then why is there an error that the ATM link is down? So some banks might have different policies, or it might be a more critical problem. It might be the case that the partitioning happened in a place that we have no data, because the ATM may not have the account balance for all customers. It may need to query a server. So if it's disconnected from that server, then probably it cannot function at all. So in that case, it has to stop working. But partitioning can be in a way that you have balance information, but you are still partitioned from the network. And that's basically this case. So if it's a more critical problem, they have no option but to stop the service. That's a good observation. But we're talking about the case that it is possible to service, but with the danger of having a little bit of old data. They keep working in that case. All right. Next example, Facebook. So in this example, Bob finds something interesting and shares with Alice by posting on her Facebook wall. Oh, next term I have to change Facebook to Meta. I have to change all the slides. So and then Bob asks Alice to check it out. And Alice logs into her account and sees nothing. The reason is Facebook follows an eventual consistency model. Although it appears to Bob that the right operation, posting on her Facebook wall, was complete, but this information was not propagated to all servers, and Facebook is in this inconsistent state for a while until it eventually catch up and perform that right to all servers, and then Alice can basically read that data. So if they wait a little bit, she can see the story that Bob shared with her, because we have eventual consistency. So, but why does Facebook use eventual consistency? Because the strong consistency is better. There's no argument in that the strong consistency is just stronger, it's just better, right? But for Facebook, if you look at the stats, Facebook has like more than 1 billion active users. So it's dealing with a huge amount of data, and guaranteeing strong consistency for so many transactions that happening on Facebook network is almost impossible. So that's why they rely on the eventual consistency, and that brings more throughput for them. So with the existing systems, they can serve many, many more users at the cost of the system being an inconsistent state. So instead of showing 20 likes for your post, by mistake for like 10 minutes, it might be 18 likes for your post. That's not the end of the world. Okay, but because eventual consistency is much more relaxed compared to strong consistency, the system can serve many more requests. It gives you much higher throughput for the same compute resources. So let's have a look at the Facebook architecture and wrap up this session. So Facebook has something similar to this. So they have memcached that works in memory, and then they have MySQL that's basically on disk, and my camera lost focus again. So, and it might be difficult to believe, but there was a time that Facebook had only one data center. So this was the architecture. So, but sorry, so let's explain this again. So if you want to basically read something, you look in memcached. If it's there, it's good. We serve from memory, so it's fast. If it's not there, we perform a SQL lookup from disk, and we also populate. We store a copy of it in memcached. So if there are more read requests for the same thing, we can serve them from memcached, which is faster. So that's the read path. And when you want to write something, you basically write it to disk. So basically you do MySQL store, and then you remove the cache copy from memory, because that would be the old value. So we remove it so that if there's some read request, they read it from the disk. So that's okay, right? So they read it from disk for the first time after the update, and they also populate memcached at that point. So if there are more read requests coming, they can be served from memcached. So that's basically the flow of data in the system. But as I said, they really had one data center some time ago, and then they realized that, oh no, we need another server on the East Coast because there are so many requests coming to our California data center. So they follow the same architecture, except that they had the California MySQL was the master server, and the Virginia data center MySQL was the slave server. So what would happen is that we need to synchronize them, right? Because otherwise they're completely out of sync. So there is like updates, right? So there's a replication lag. So if we update something, we propagate it to the other server, okay? Now, something bad can happen in this system. How? So a user updates first name from JSON to monkey. Okay. Then they write monkey in the master database in California. So I told you that if we write something, so we update it in the server and we remove it from the cache, right? So we remove it from memcached. Memcached is a distributed system, so we remove it from both places. So we update this thing, so which is changing name from JSON to monkey, and so that is executed in the California data center, and we delete the cache. And as I said, there's a replication lag. So with some delay, this update will be replicated in the Virginia MySQL server. But because of this lag, it's possible that somebody, before this replication arrives at Virginia data center, somebody performs a read request. So somebody requests to read the profile, to JSON's profile. What happens at this point? So the memcached is invalidated, so we cannot serve from cache. So we go and read the data from the MySQL server and pass it to this person. And remember that this update has not arrived yet, so this would be the old value in the system. So this would be JSON still, because I haven't got the update yet. So what happens is, if I told you that if you perform a write and if it's not in memcached, we also put it in memcached. So what happens is we read the old value and we also update memcached with the old value, because that's how it works, right? Whenever you read something from MySQL and it's not in the cache, you also put a copy of it in the cache. Now, after a while, this update will arrive eventually at the slave MySQL server, and it updates the value to the new value, which is monkey. And we are done with the update. What is the problem? The problem is that the cache still has the old value. because of this synchronization problem that we had. Because before we get the update, we read data, we populated cache, and now the replication arrives finally, and we update, but the cache is still reflecting the old value. And if somebody queries the Virginia data center, what happens? Because the data is in the cache, we will serve from cache. So if there's a read request, we reply from cache. So we keep responding with the old value forever, not forever, until there is another update so that we invalidate the cache in that data center. But until then, we will be using the old value. So Facebook figured out, okay, that's a problem. So what they did, they just they did like a dirty hack. They just piggyback some data on their replication system. So they said whenever we basically replicate something to the slave server, we also set a dirty bit. Okay, so we also set that dirty bit, and basically that bit prevents the system from using the old value. So when you want to read something, you see that the dirty bit is set, you don't rely the cache value. You read from this. That's the idea. So they fix it. So as you can see, when we have eventual consistency, there are some complications like this that can happen, and they're pretty difficult to debug. So the last thing I want to talk about is this concept that everything is designed based on when partitioning happens. So the whole system design is based on, okay, if there's partitioning, do I choose consistency or availability? But wait a second, like 99.9% of the time, we are not in that situation. We're in the like normal situation. So it looks like we have designed a system for the worst case scenario that doesn't even happen 1% of the time. So this design decision can hurt the system, because like most of the time where there's no partitioning, the philosophy of the system, the way it works, is based on when the system is partitioned. That can hurt the performance significantly. So you optimize the system for that 0.1% of the time and not 99.9% of the time. So people realize that the actual trade-off is not between consistency and availability, but rather between consistency and latency. And it includes availability, as I will explain in a second. So as I said, because of the possibility of failure, we designed this, but the problem is most of the time the system is healthy and it's okay. So it's better to consider latency instead of availability. It's nice because it covers the cap theorem, because latency captures availability. What is not having availability? Infinite latency, right? I can say, yeah, the system works, but with infinite latency. That means there's no availability, meaning that the user should wait indefinitely to get the results. And that's not having a service. So latency is actually better, a more general concept that helps us to optimize the system, even when the system works just fine. And not just think about what happens when things go wrong. So a new theorem was introduced called PASELC. PASELC includes the cap theorem, but it also talks about what happens when the system is healthy and everything is fine. So this is how you should, so this also stands for the name. So it says so it defines the behavior of the system, but it's much more complete than the cap theorem. What does it say? It says if we have partitioning, and the first piece for that, it says if there is partitioning, do you choose availability or consistency? So this part is exactly like the cap theorem. But it also has another part. Else, when there's no partitioning, when the system is just working fine, do you choose latency or consistency. So it's a more complete version of the CAP theorem. In addition to figuring out what happens when the system is partitioned, it also talks about the behavior of the system when everything is just fine. When everything is fine, the trade-off is between latency and consistency. If you want to have very strong consistency in your system, your latency goes up. If you choose eventual consistency, your latency goes down. So there's a trade-off between latency and consistency. The better consistency you choose, you have to pay with latency because a strong consistency needs something like two-phase commit. You have to wait. You have to wait for it to happen. So it increases your latency. So that's an interesting system. And basically it says, okay, this is the CAP theorem. When the system is partitioned, you should choose between consistency and availability. But like 99% of the time, the system is just working normally. So the trade-off is not between consistency and availability, but rather between consistency and latency. So final slide, let's see some examples of common systems and see their pass-elk behavior. So we have PAEL systems. Okay, so they choose, so when they have partitioning, they choose availability. In normal case, they choose latency. It means that they always give up consistency. They always give up consistency. Either they are partitioned or work in normal condition. So they care about latency and availability. They care about throughput. They care about supporting more clients, decreasing the delay. And examples of these are Dynamo, Cassandra, Riak databases. Okay. On the other hand, there are systems that refuse to give up consistency. So if it's partition, consistency. Normal situation, consistency. So they prefer consistency over latency and partitioning. Examples of these systems are Bigtable and HBase, we learned recently. So they are always in consistent state. So at the cost of higher latency, less throughput. There are systems that behave differently when they're in partition and a normal situation. So these systems, when they are in normal conditions, they choose consistency. So if the network is okay, everything is okay, the system supports strong consistency. But if we have partitioning in the system, they switch over to availability. They keep working. They say, okay, I can no longer provide consistency, but I continue my service. I don't stop my service like the previous case. These guys would stop their service, right? Because they always pick consistency. But they say, no, if there's partitioning, I prefer availability. I continue working, but I switch to a lower consistency scheme, like eventual consistency, for example. An example of that is MongoDB. That's, you might have heard about MongoDB. So that one is in this category. And finally, the most strange category is this one: systems that in normal condition, they care about latency. So they give up consistency in normal condition. But when they are partitioned, they don't give up consistency, okay? So that is strange if you think about it. And the only system, as far as I know, that belongs to this category is a very old system. I don't think it's around, still around. Is Yahoo Peanuts. So this system has this very strange behavior, and I'm really glad that this category exists, because otherwise I didn't have anything to put here under this bullet point. And that wraps up this lecture. So we have 2 more lectures to go. Questions? So, but why would anyone want that? A good question. I knew the answer. There was something bizarre, a bizarre requirement when they had this system. I believe you're talking about the very last category, but I don't recall why they did this. It was a bizarre situation as far as I remember, but that's how they they decided. It was for a particular application. It was for a particular application. Let me look it up again. I forgot exactly what that application was that they designed it this way, that when they had partitioning, they would basically stop. They would stop because for some reason when it was working normally, it was fine because they would say the update propagates in a second or so. But when we go to partitioning, it's not known. Is it going to be a second of disconnection, a minute, or an hour? We don't know. So they would stop completely. I think that makes sense. But again, I don't exactly remember what the story was. And the system is not around anymore as far as I remember. So, but that's just for the purpose of having something in that category, which is very unlikely. So we don't have systems really in that last category. All right, let me stop recording. So goodbye to the people of YouTube. And you guys feel free to leave